So we will move forward with the hands-on session by Mr. Biraj Kharga. So over to you, Biraj. You can start the session.
Hello everyone. So today I'm going to demonstrate two multi-phase problems. So before that, I'm going to share a link where you have a tutorial video as well as the case file. So you guys can download now. First of all, just click on the video multi-phase modeling in OpenFOAM VOF. So in that video, the case folder and the geometry are described in detailed way. So make sure to click that video first and understand what the case is. I'm going to demonstrate after maybe like 20 minutes. I hope everyone has seen the video. Now I'm going to demonstrate to everyone. Please go to the download folder where you have downloaded and go to the BOF. I think I'm unmuted, so I'm going to do from the first. So what I did is, so everyone, please go to the run directory. I type the run command. So inside that, I have already pasted the BOF bubble folder inside the run directory. So I'm going to press this command. So cd BOF bubble. So you can type tab in order to complete the command. So I'm inside the BOF bubble. So is everyone done until this process? Type is if you have completed until this process. Now, what are the files? So let's type this command. So ls space asterisk. So if you put this command, so it will give inside the zero folder, there is alpha.water, which is the volume fraction or phase fraction of the water, which is the original, which is the initial condition, and PRGH. So in the VOF, the PRGH file is required, not the pressure. So this is the pressure without the hydrostatic component, as you have already like get that information from the video. And another one is the velocity boundary condition. So inside the constant, there is Z, which is gravity file. So if you have to mention the value of the acceleration due to gravity, so you can mention in this Z file. And in the transport properties, so you can define the kinematic viscosity of the different fluids. Like let's say if there is a water or it's or air. So if you have a two fluids, namely air and water, so you can give the kinematic viscosity and density in this transport properties file. And in the turbulence properties, you can mention if there is if you want to mention the turbulence model like K epsilon or something, or even the laminar simulation, you can mention here. So in the block mesh stick, you can mention the you can define the mesh, like how much division and grading and the patches. And in the control trick, the you can define the end time, start time, maximum current number. So those kind of information you can find here. And for the FV schemes, what kind of schemes do you want to solve for the discretization of the equation? Like let's say there is a gradient scheme, Laplacian scheme. So you can define here. And in the FV solution, what tolerance would you like to give? What relaxation factor would you like to give for the parameters? So you can define here. So this is the new term. This is a new file, which is set field dict, which is common file used in the multi-phase flow, namely in BOF, even in the Eulerian approach. So in the set field dict, you fix the field. Like let's say if there is if you want to define the volume fraction of water in a certain region, so you can define here. So let's go there. Let's first go to the mesh, gedit system. Inside the system, you can go to the block mesh. So you can see the block mesh disk, right? So only one block is given for the this bubble column. So we don't need to define more than one block. So 100 division is done in the x-axis, 150 division in the y-axis, and one in z-axis. And simple grading, we have not defined any other grading except one. And for the edges, there is no any edges. So for the boundary, we have walls and the atmosphere. That's it. Atmosphere is the top part of the bubble column, while the rest of the patch is walls. And okay, and we don't need to merge the match pairs. So it is empty. So after that, close this, and let's go to the boundary condition. Gedit 0. So type this command. I think you have already familiar with the Linux command. So you can type this command in order to view the velocity boundary condition. So in the wall, no slip boundary condition is applied. So this is like straightforward. And for the atmosphere, we have given the pressure inlet outlet velocity condition. As Jananima has already given you the information, what's the pressure inlet outlet velocity is about. So if you define the pressure inlet outlet velocity, so you need to give the total pressure boundary condition in the pressure PRGS file. So that will give the well-posed problem. Otherwise, if you define other boundary condition, you may get some error. So that's why these two boundary condition match the best. So the default phases is considered empty. So I'm going to close this. For the P RGS, we don't have any P file. The P is derived from the PRGS, where PRGH equals to P minus rho GH. So in case of buoyancy flow, in case the body force acts significant, so we need to define the PRGS. I think you guys have like problem regarding the differentiating between the PRGS and P file. So I think that clears that out. And for the walls, we have given the fixed flux pressure. So what it does is it sets the pressure gradient to the value, so that that flux is coming. That flux is calculated from the velocity boundary condition. So it set the that pressure gradient. So and the value is given uniform 0 for the initialization. So it is just a placeholder. And for the atmosphere, we have given the total pressure, and the total pressure is given as uniform 0. So if you define the pressure inlet outlet velocity, you have to define the total pressure. Okay. And the rest of the phase is defined as empty. Now let's go to the alpha 0 AL alpha dot water dot origin. So initially, like we have defined the uniform 0, and it doesn't have it is dimensionless, so no dimensions. And for the walls, the 0 gradient is given. So as we know the surface tension between the wall and the interface, we can also give the constant alpha contact angle, which is 90 degree for this case if we neglect the surface tension between the walls and the interface. And for the simpler boundary condition, we can use the 0 gradient. Otherwise, you can also give constant alpha contact angle. And for the atmosphere, it provides a generic airflow condition with specified inflow in case of reverse flow. If you think there is a reverse flow, you can use this boundary condition. If there is a reverse flow, if you just type 0 gradient, then the solution will crash in that case. So make sure you do this. And for the default phases, it is considered empty. Okay. Now let's go to the constant directory. Transport properties. So in phases, we namely have the fluids, water and air. So water is defined first. So you have to define alpha dot water, and also even in the set field dig, you have to define the alpha dot water, not the air. But if you define the air at first, then you have to define alpha dot air. Okay. For the water, Newtonian transport model is used, and the kinematic viscosity is 10 to the power minus 6, and the density is 1000 kg per meter cube. For air, same. Newtonian transport model is used, and the 1.48 into 10 to the power minus 5 kinematic viscosity is used, and namely 1 kg per meter cube is only defined as a density of the air. And sigma, so this is another term which is surface tension between the water and air. So it is 0.07. I think everyone has. So okay, understood until this process. Okay, let's go to the system and control D. Only thing I want to mention is in the application we define as interform. Rest of the information we can see in the people form as well. But the difference is maximum alpha Courant number. We have set 1. So if alpha Courant number gets above 1, so it will limit that. So we have to define this. And adjust time step is it's set S. So if you define maximum alpha Courant number 1, maximum Courant number as 1, so automatically if we set S, then it will adjust the time step. Like let's say 0.001 or sometimes 0.005. So yeah, it will set based upon these values. If you can also even define 0.8 for the maximum Courant number. Now let's go to the set filtering, which is one of the important file. So the default field values. So in the column, so we have set the default values as alpha dot water as 1. So in the bubble column, we have defined entire volume as 1. Means it is entirely filled with water. But there is some section where we have to define the bubble. So first of all, type regions, and inside regions, you have to define cylinder to cell. So I think Haris has already mentioned about cylinder to cell in the toposet. So it is the same. It works the same way. Like you have to define the 2 points and the radius. So the initial point and the final point for the cylinder and the radius. And in that region, in that cylinder, the alpha dot water is 0. That means the air is fully covered in that region. And where we also have to define a cavity, air cavity. So in that case, box to cell is needs to define. And in that case, the maximum XYZ value and minimum XYZ value and maximum XYZ value needs to be defined. And in that case also, the alpha dot water is considered 0. So that means alpha dot air will be 1.
That P1, P2, the why 2 points is required, because 1 point
Okay,
is
okay.
okay.
So in order to define a cylinder, so we have to give the 2 points, right? So let's say this is like, can you see my cursor?
Yes, yes.
So this is like a cylinder. So you have to give the 2 points in order to define the height of the cylinder. So this height 0.001. 0.001 is the height of the cylinder in the z-axis. And the radius, you also have to give the radius, right? So the circular radius is 2 mm. Okay. Understood? But for the box to cell, the nomenclature is a bit different. You have to give the minimum XYZ and the maximum XYZ. So that is the only thing. So we are all set. Now we have to first generate the mesh. For that, you already know block mesh needs to be generated. So block mesh, the number of cells is 15,000 only. So a bit closer. And after that, set field. So we have, so the difference is you have to define the set field command. So it will set the value. See, setting internal values of volume scalar field alpha dot water, because this is the default values we have given in the set field dict. And other than that, we have also defined the reason where we need the alpha dot water as 0. So that means it will be filled with air, the box and the cylinder. Okay. In order to define the cylinder, the 0.1 and 0.2 means the upper cylinder and the lower cylinder points and the radius.
Excuse me, what you have done now? Meaning, after you are looking at all the files, what you have done?
So what we have done is we have pressed this block mesh command.
Oh, blockers.
Yes, correct. Because in order to run the mesh, block mesh has to be generated. Any mesh, you can even import the mesh as well. So if you have to if you have to import the mesh from Fluent, you can use Fluent 3D mesh to form and give that MSH file name, and it will automatically generate the mesh in the polymesh folder. So it does the same thing. If you generate the block mesh, so you can see now ls and asterisk. So you can see polymesh has been already generated because I have already used the command block mesh. So polymesh has been
Oh,
already generated.
okay.
The points, faces have been already defined in that polymesh. Understood?
Okay. Thank you.
Okay. Now after that, we need to solve, right? So in order to do that, we have to call the solver name interform. Now it's running. The case is pretty simple. It will take like 1 or 2 minutes. Meanwhile, you can also even run in your system. If you have any doubts, please feel free to ask.
Sir, exactly. We have tried first block mesh, then we
Yes,
have typed set field, or
correct.
after block mesh set field, then interform, right?
Interform,
Three.
correct, correct, correct.
Okay. Thank you.
The SET, like F capital IELDS. Okay, set fields.
Yes.
If you don't know the commands, just write tab. See, CSET, type this, and if you don't know the spelling, just type tab. Just press the tab, it will automatically complete the command.
Okay. Okay. Okay.
Now, okay, the simulation has already been done. So let's type paraform. Now I'm going to show why like we have to define the two fields. So in order to see that, I will wait. I will wait. Go to the VTK block colors, okay? And go to the alpha dot water because this is the multi-phase. So we want to visualize which part is the water, which part is the air. So as you can see from the label itself, so this is the air. See alpha dot water, the value of alpha dot water is 0 here. So this is cylinder to cell. So if you visualize in 3D, so this is like a circular and this is circular, right? So if you visualize in 3D, it will be a cylinder. So we have to define the like center point of this point, let's say this point, and we have to define this point and the radius. The radius. I think someone has asked why we have to define the.
Yeah. Thank you, sir.
So I think I think the doubt is clear, right?
Yes, sir. Thank you.
Okay, that's why like, and box to cell. So box to cell is this. So we have to define this cavity as air. So we need to define box to cell. See, this is like a box, right? And this is the cylinder. Otherwise, entire domain is water. So we have defined in the set field is entire domain is covered with water, and from that domain we need this cylinder to cell and this block cell as alpha dot air. So this is the
Yeah.
initialization.
Basically we are patching the regions inside.
Yes, correct. We are initializing the field. So this is this is at the 0 time. Now let's see what will happen in the next time step. Like slowly see, like, okay, let's.
Sir, I want to ask
Okay.
here, what if it is a 3D? If it is a 3D, then we have to put a sphere, right? We are
Yeah.
doing this one considering it is a 2D.
Yes, we are
That's
doing.
why
So that's why
yes.
we have put the default faces as empty.
If it is a
So in order to define the sphere, there is also a command which is sphere to cell. Okay.
okay.
Yeah, in order to define the sphere, there is also another command you can use, sphere to cell. So you can Google it. You can find the syntax.
Okay.
Okay. So let's see what will happen. Slowly, the bubble is rising up and it goes to the surface. So this is what we are simulating for this case. The bubble slowly wobble up and go to the surface flow. Due to the buoyancy, the forces, right? The gravity is also acting. And this is, if you also want to see the PRGS, see. Because why we need PRGS is the BOF solves the momentum equation in PRGS format. It doesn't solve in like, I also want to show you the source code. So the U equation. So this is, see, I think John sir has already mentioned. Go to the cpp.openform.org. So you can find the source file. So go to the U equation and go to the source code of this file. So see, surface normal gradient of the PRGS. While solving the momentum equation, it will solve this PRGS. So that's why it is needed for surface tension force. This is the body force. And here ddt rho is defined. Turbulence, this. I think it is here from the equation. Now I'm going to, I think everyone has simulated this bubble rise problem. Now let's move to the next problem, which is a dam break simulation.
Sir, how can we just save this animation or animate this?
Okay,
Rising?
go to the save and go to the file. See, go to the file and save animation and OGB. There is no MP4 because this is the older version of ParaView. In newer version, there is also .mp4 format, so you can save in that. Now now just save in the .ogb format. Just type alpha. Okay, this is the PR here. See, okay, alpha dot water. Okay. So file, save animation, volume fraction, water. Okay, and this option will be shared. So you can define frame rate as 1 or 2, even more than that. So for me, like I would just set frame rate as 1. So it is exporting. It is exporting. Okay. Now it will save inside here this UF bubble. So you can see volume fraction water dot OGB. So this is it is going very slow because, as I have said, only the frame rate as 1. You can even set frame rate more than that. This is how you can save the animation.
Okay, sir. Thank you.
Okay.
Hello, sir.
Yeah.
So can you explain what is this inlet outlet boundary conditions? So what exactly are the conditions for that?
Okay, for the, so let's say like for the alpha dot water, right?
Mhm.
I will show you alpha dot origin. This the inlet outlet condition. Like in case if there is a reverse flow, then it will supply the it will apply the inlet value, which is a fixed value.
Okay.
And otherwise it will give the zero gradient boundary. This is a very flexible boundary condition. So you won't get the like numerical errors, and the simulation won't crash if you use this kind of boundary condition in data out.
Okay. Understand. Okay.
Yeah.
Okay. Yeah. Thank you, sir.
This is a hybrid. Like if you go to the source file, type SRC and type zrep this inlet outlet, right? Inlet outlet. Maybe you can find. See, there are lots of. So it is defined in lot of files. So just go to the FP patch field, and there is a derived. Okay, finite volume field. This okay CD finite volume patch. Go this fields. If you want to search, just type this command.
Okay.
Finite volume fields, FP patch fields, F fields, FP patch fields, and go to the thing derived, and there is so many boundary conditions. See, inlet, outlet, free stream, So you can find like pressure inlet outlet velocity, you see. So you can go to the source code and see like what it does.
Okay,
Okay.
I understand. Okay, thank you, sir. Yeah.
Nothing
Hello,
in the
sir.
open form is black box. You just have to find it.
Can you show the paraview once more?
Okay, paraview. Okay.
Anyway, after 0.3 seconds, the interface between air and water is changed, right? After
Alpha dot water. This?
after now after 0.3 seconds after this, now the interface is wavy like this. So can you capture the interface like a curve or something?
So like you want to increase the end time
Capture the interface. Capture the interface.
for capturing the interface like this.
It's a curve, right? It's a wavy.
It's a wavy, yeah.
So can you plot it on a graph like the interface?
Like plot over time or something.
Plot over the height and maybe radius.
Like I
The
don't have
height
that.
of the interface from bottom. Height of the interface from bottom.
Okay, for that case, like I don't know that. I need to explore that in order to get
Okay.
that height. Also, you can do what you can do is like get the volume fraction data from this domain and export it in the CSV and do the analysis. Maybe from that, because in the interface, like you can see, like this is the 0 alpha dot water and this is the 1. So you can do the analysis from there.
Okay.
So now let's go to the another tutorial. So in that folder I have already given. So you can go to the PDF file. So downloads and UF. So you can see dam break simulation. Now we are going to do the dam break simulation. So you can start. You can look at that handout and follow the process. So if you have any doubts or error, I will demonstrate after like 10 or 15 minutes. And there is also a problem at the end. So I want to make it interactive. So make a water level same as the height of wall without changing any other thing. I think there is some typo. So any other thing and simulate what will happen. So this is a classwork for you. First simulate this step and after that go into this. If you have any problem regarding the bubble rights, so you can place your queries in the chat or even unmute yourself.
Hello. Exactly, I have a question that regarding that PRGH, that part, that's pressure one, pressure that's file, that's a
Yeah.
pressure RGH file. That's one also winning previous one and this one. I want to ask that's top boundary condition that's we are putting atmosphere. The name is atmosphere. In that one, if we can see that previously also we have given some that boundary condition or the name is total pressure or something we have given.
Yes.
Here also in this case also when I am seeing it, meaning I am talking about this dam break.
Correct.
Here also I am getting a break. It is a total pressure. My point is here that why we are giving that total pressure. My point is if I will give it fixed flux pressure also, what the problem it will happen, because the pressure is not going to affect to that top. Why it is so? If it is changed to the left, right, and bottom boundary cutter shape, then what the difference?
So in order to distinguish between the walls and the atmosphere, so we have given the fixed flux pressure in the walls. So all 3 walls are enclosed, right?
Yes.
In that case, like what it does is the pressure gradient is set from the like such that the velocity flux will come from the velocity boundary condition, because we have defined in the no slip condition. But in case of this atmosphere, we don't know the velocity. In the no slip, we know that in the wall, we know that velocity, right? Because there will be 0. But in the atmosphere, we don't know that. So in order to model that, we can give the boundary condition such that it will be okay for both pressure condition as well as velocity condition. So in that case, total pressure needs to be defined.
Okay. And the pressure P0 value we are giving at uniform, it is 0.
Yeah,
That's
that
the
is
thing.
0, P0, which is total
Have
pressure.
you have you remembered in that previous one we are given value uniform is equal to also 0. We have written that in previous code. We have given in that third line will be their
This
value. Same thing we have written it in the previous code also.
yeah.
That's meaning 3 lines, but another line was written value uniform is equal to 0 also.
Yeah, for
Why
the
this value is written? If what is the difference between that value uniform is equal to 0 and
okay.
you want
I will explain. So in this case, this is for the initialization. The value is given for the initialization. For to even run the simulation, you have to initialize, right? So
right,
this
right.
is the initialization. But in this case, P naught is the total pressure is 0. So this is a bit different. This is not for the initialization. This is the total pressure is considered 0 as a like boundary condition. This is this is set. The P naught is set as 0. Understood?
Okay. Meaning it is a combination of boundary condition and initial conditions.
Combination. No. I'm just telling that for the atmosphere in the velocity, what is the boundary condition? Can you see? Can you say? Is it pressure inlet outlet velocity?
It is at the boundary condition for
Velocity.
velocity will be there is no velocity is not been given,
Pressure
right?
inlet outlet velocity. See,
Yes.
I have mentioned. So if we define this pressure inlet outlet velocity, we have to give the total pressure boundary condition. I will also show you the CFD online. In that case, yeah, just see. High pressure inlet outlet velocity boundary condition are to be used with inlet outlet boundary condition for the U field, and you use total pressure and fixed value for the P field. These boundary condition guarantee a well posed problem. So in order to like solve the boundary condition error, so this will guarantee a well posed problem. In case we have like pressure measures and the backflow expected, if there is a reverse flow or something, like we can use this total pressure and pressure inlet outlet velocity boundary condition.
Okay.
So I've used the same thing.
Okay. Thank you.
Yes, Steve, as mentioned, like, can we refine the case? Yeah, certainly. I can show you. Like, it can take a longer time than the previous case. So what I would do is copy this, go to the run directory, cp r uf bubble, and what I would give is refined uf bubble. So let's go to refined uf bubble GAD. So in order to change the mesh, you already know, we go to the block mesh, and what I would change is like, let's say, multiply by 2, okay, 200. It will be very large. Previously it's 100, so I would give as like 150, and this as a 240. Okay, just change this. Okay, so I already saved it and close. Now what I would do is parafoam, no, foam clean case, in order to clear the case, and block mesh. Now the number of cells has been increased. See, 36,000. Previously it was about 15,000 or something, right? Now it's 36,000. So it has been increased. So it will take a time, longer time. So it fills and interval. I don't think there is much difference between the previous solution and now current solution. Let's see what will happen. Still running. It's taking a lot. the exact
Biraj, in those comments only I have something to ask. In those
okay.
boundary conditions, there is every time we are writing inlet, for example, type is inlet outlet.
Yeah.
Then inlet outlet uniform, we are writing uniform 0. If it is a non-uniform, for example, in
Hmm.
that boundary that some portion is different, other portion is something different. So how it can be written is there uh, in
Yeah,
that?
non-uniform can also be defined, but like along the path, we have to define like in order to define like the same value, we can define it as a uniform. Otherwise, you can give other boundary condition as well, non-uniform as well. Like non-uniform means like let's say a parabolic boundary condition, something like that.
Yes, meaning what are the boundary condition? How we will define, and they are only how we will write it. Any give me any hints, meaning how
Okay, okay.
generally?
I think you were present in the like yesterday's session. In that session, John sir has mentioned how to define the parabolic inlet velocity. So in order to do that, you have to do the coded fix, code stream or code type coded like programming in the boundary condition and give the parabolic inlet. I think you have missed us
Okay,
something like in order.
meaning maybe
Yeah.
that one. That is one thing. Second thing also, when we are discussing, you can see that in that whatever I have asked you, maybe it is in that PDF only.
Mhm.
First, second line, second page in the atmosphere, it is written type is inlet outlet, then inlet value uniform is 0. Then it has written value uniform is equal to 0. I mean, my question is inlet value, if anything has been written, then why again the value uniform 0 has been
Okay,
writing it
okay.
again? So why it is two things?
Mhm.
That's the question previously also I have asked. But my point is, what is the difference of having those two?
Okay, okay. So let's see, the value is just for the initialization, but the inlet value is in case like if there is like there is an like out for inflow, right? So for if there is an inflow or like let's say if there is like a reverse flow, then it will define as a inlet value. So in the alpha dot zero, right? This is mentioned in the alpha dot water, right?
It is alpha dot water. Yes,
Yeah.
yes,
So
yes.
inside that alpha dot water, the velocity of water will be zero, which means we have specified the inlet value as zero, means the 100% will be the air, na?
Exactly. I am not understanding this. I understand the inlet values is 0. That means
Yeah.
it is the initial condition has been that's has been giving that at the boundary condition that's inlet values will be 0. Then what? Why the again we are writing is value uniform is equal to 0 is 0.
Okay, value uniform zero is for the initialization. This is how this boundary condition works. If you go to the syntax, if you don't give this value uniform zero, then it will show an error. Why value is not mentioned, value keyword is
Uh,
missing. So it will show
so
that error.
should I add to this point, Biraj? Like,
Yeah.
I want to add.
Okay.
Actually, this inlet outlet is a derived class from
Mm.
zero gradient. So since it is a derived class, so it's inherent the properties of zero gradient boundary also. So that's why it will give a code error of value if you don't define the value syntax. But it's not like it is playing a part in this boundary condition. It's just a C++ thing.
Okay, meaning it is it has meaning it will be generally written like that, meaning you have to give this then you have to write it value uniform is equal to 0
Yeah,
something
yeah,
like that.
it's the syntax for this boundary condition.
Okay, meaning because why this one someplace it is values has been writing it, someplace we are not writing it.
If that is the inlet outlet boundary condition, then might be it is been written always, or maybe like or otherwise like internal field in the value like that it will be written. Okay.
Okay, 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 okay. Thank
So as you can see here, like see type indeed outlet and indeed value, and the value is given. So optional entry is this, but this is the mandatory. See, as you can go to the like user guide to 2112 or even the CFD foundation. So this is the mandatory requirements, as Krishnakant has already mentioned.
Okay.
Still running. So let's go to the Paraform. You can even see the mesh. Refined. Surface utilities to see this. So you can see it is very refined. You can even go give the grading, like you can give the fine mesh in near the wall, right? You can do that. Let's see the alpha dot water and of this. So this is the result.
Hi, Biraj. If I want to see the vertices also, the points in paraform, so how do I do that? Like,
Okay, paraform, type paraform.
Yeah.
Block.
Okay, hyphen block.
Okay. Apply this. See, you can see the vertices, right? 0, 4, 1, 5, 2, 6, 3, 7, right?
Okay. And one more thing, like if I have to see the axis like with the values also.
With the values, okay, nice. This is a nice question. So, access. Go to this properties tab.
Okay.
And there is an access grid. So you can see the values. See, 0.03. So this is the 0.03, right?
Okay.
And in the 0.024, there above this y-axis line, there will be a air cavity.
Yeah, I understand.
If you see this, I think yeah. So there we have already mentioned in the set field as well. So you can see, like you can play around and check.
Okay. Yeah, I understand. Yeah, thank you.
Now foam clean case, because this is taking much space. Now what I would do is just copy the tutorial for the dam brick case. Okay, I think some of you have already done the dam brick. And did you also do the problem like I have given to you? If you have, like, type case in the chat, and you can even share the screen. Like what is the result if you make the water level as same as the wall interform. And after this, I would go to laminar and dam brick. Inside dam brick, there is also a dam brick. So this and dot. This is the destination folder. So type dam brick. So what? So I have already defined the boundary condition, right? So there is nothing, no changes. Only changes is the system and set field. See, the initial the default value is 0. We have given. I will also show you the. I would like to show you side by side. A pair of blocks mesh. I have to give a reference, and so block mesh. Okay. So see, we have 5 blocks. One, like if I give you the blocks, then 1 and 2, 3 and 4 and 5. If you want to visualize the block, yeah, I would do is block. See, there are 5 blocks. 1, 2, 3, 4, 5. Right? And these are the vertices 0, 12, 4, 16. So where the block is defined is go to the F9. Go to the block mesh stick system. Block mesh stick. So see, there is 5 blocks. 1, 2, 3, 4, 5. So in one block, 23 in x-axis, like 8 cells in y-axis, 1 in z-axis, right? So these are defined in the block mesh stick. So it is shown here. So if you want to see the surface with edges, I think to read color, I think we can't see it. In order to see that, what we do is parafoam. Okay. Because after the parafoam block, you have to again type block mesh. It will get deleted, I guess. Type parafoam. It is it. So if you want to see the cells, here it is fine, a bit fine compared to this. This is a bit coarser. So what we did was like go to the set filtering system. Set fill. So the entire domain is initialized with alpha dot water as 0, which means it is filled with air. This entire domain is filled with air. Okay. And what we define is box to cell as this is the minimum XYZ value and this is the maximum XYZ value. And where we define as alpha dot water as 1, which is the maximum alpha, right? This is the maximum alpha the water can get. So this is the one we have defined. So what it means is, so in this portion,
so like, can you show that set fields did like the alpha dot water one, like in
correct.
box
I would do that. After running the set field, I will only able to do that. Whereas set fields YF9 set fields. Okay.
No, what I'm saying is, can you show that that file?
Okay, file. Okay. File is system set field. Okay. Yeah.
So in this one box to cell, like it's the Z values are -1 to 1, like because but like our blocks are within the range of 0.1, 0 to 0.1, right? Why this -1 to 1 is there?
Okay, let's see for that. Let's see in this case. Let's go to the parafoam. And give the access. You just said is zero to
we can check it in that the block mesh dict also, right? So there we have defined the Z. Yeah, here see 0.1 is there.
so yeah, in the block mesh we have given 0 to 0.1 na? And for the set fields we have given 0 to, if I go to the
-1 to 1,
like -1 to 1, right? It doesn't matter. Like if you even give this 0 as a 0, then it will do the same thing. I think there is some kind of error. Like we can even do the 0 to 0.1 as you have mentioned.
Hello, Chaitanya.
Yes, yeah.
Yeah. So the thing is that set fields dict, right? It what it does is it selects the region, as see Biraj is showing now. It selects the region. It selects the cells. When the command is box to cell, it selects all the cells which lie within this box. So when you are defining the box, right? For you, the X and Y coordinates are main because they are in the mesh. The Z coordinates are outside. So Z value, if you give anything even larger than 0 and 1, it will not matter, right?
Okay, understand.
Like you're sweeping in that domain, in that region, and whatever cells come, they come. So if you give, say, as Biraj said, if you give 0 to 0.2, then also it will work fine. If you give a large value, you don't want to think, okay, what will it be in the z direction, then also it's fine. Because what matters is this x and y coordinates.
Okay.
Did you understand?
Yeah, understand. Like it selects all that is there in that box. Like
Yeah.
understand.
All the cells, whatever is there in the block, it will select that, and for those cells, it will set the alpha dot water as 1.
Okay.
So only the cells which are lying in this box. So
Okay.
for this box, our x and y dimensions are main. The z dimension can be large, anything larger than the thickness of the
So
block.
like the way it is creating box from these dimensions. So these are all these two are diagonal vertices. It's like that.
Yes, diagonally opposite vertices, so that it
Okay.
it spans the entire box.
Okay.
Okay.
Yeah. Thank you.
You can even give the 0 and 1. No, like the result will be the same.
Okay. Yeah. Thank you. Understand.
Now after that, the set field has already been done. Interform. Okay, now it's done. If you want to see the result, apply it and click on alpha dot water. So this water level will outside this wall as well. So what in the next problem, what I would you guys would do is like make the water level same as this. Like initially this water level is a bit high, so that's why it goes it like passes this wall as well, right? But like make the water level same as this height. Just don't change the x and z value. Just change it. Like to do that, what do we need to change? Can anyone answer? If you have already simulated that, you can even share your screen and tell how you did that. Does anybody solve that problem? Like I have given to you. Make a water level same as the height of this wall without changing any other thing and simulate.
That height is 0.328. I think I like from block mesh dict I can see it's 0.32876 something. Maybe
Like
that,
how did you calculate?
like yeah, so because this block one like so it is 0 1 5 of like that, right? 0 1 are the like bottom and 5 is the height of that first block, right? Then I went to that fifth vertex and then it is 0.32876, right?
Yeah. So I think like if you have missed, like I think you missed the point. I think there is something you need to check. Like what is the thing? You are correct, but partially correct. Does anybody have any answer about it?
Also, I have one doubt regarding this. So when you are showing the like no that figure in open form,
Yes.
so yeah, I can see height as somewhere around 0.56 something, but like in the block mesh dict file, I can see the maximum height as like 4 mm.
That's correct. Yeah, you are like you are giving a hint. Like what is that? Yeah, you are like you are asking the same question, but the answer is same for both of the cases.
Okay.
I will give you like 1 minute, like to figure it out.
Okay, I see a convert to meters is 0.146. I think that factor has to be accounted.
Yeah, correct. Yeah.
Okay,
So
okay, understand. Thank you.
So what will be the water level?
I think that 0.32876 into multiplication by like 0.146. That I will
Yeah,
get it.
correct. So yeah. So where do you like plug that number in?
And set fields dict.
Yeah, you can simulate and share your results
Okay,
on the
okay,
screen.
sure.
Yeah, do that. I think everyone has got what I meant. Chetan, are you simulating?
This I'm simulating. Yeah.
Yeah. If you are done, like you can share a screen, like just unmute yourself. I will give the sharing option.
Yeah, I just changed the file. Like I think I have to run it now. So yeah,
Okay.
one.
Do that.
So I have simulated, but like that water is not moving actually. So but the height is same. I don't know. Maybe I missed something.
Yeah, you can share your screen. Like let's
Yeah.
see.
Okay. This is what I got. Like, but when I do it, nothing is happening there.
Can you close that para view?
Yeah.
And the type LS. What you missed was reconstruct path. Do reconstruct.
Oh, okay.
RECONSTR. Tap. Yes, correct.
Okay.
Now you will get the result. Type okay. Close that and apply.
Yeah.
Now you are getting right.
Right.
See, the water doesn't
outflow.
Doesn't cross that wall.
Yeah, exactly. Okay.
So what you did was just go to the what you did. Show them to the participants as well.
So I went to this set fields dict and I changed this value here, the y value.
Yes,
the minimum value, this value. I think that's the height of the dam. So
and also
this is the value I calculate, that 0.32876, that height into that multiplication factor. So
also show them the block mistake because they don't know how that 0.1.
Yeah, the way I have done is like this 0, 1. So I have seen like how these vertices are there in that block. So yeah, and then like 0, 1 is the bottom points and 5 is the height of that dam, right?
Yes.
So and I have to go to that fifth vertex, right? And 0, 1, 2, 3, 4, 5, like this the height.
Yeah.
So like from here I have got the height of the dam and then
multiply with the 0.146. Yes.
Yeah.
Exactly. So that is how you obtain the y value and put that number in the set fields. So that will be Yeah, that is how we do it.
Yeah.
Okay.
Yeah. Sure.
Thank you, Chaitanya.
Yeah. Thank you.
I think everyone got like the results after changing the water level height. So I would like to hand over the session to Payal ma'am.
Okay, so any feedback on this session? Any more doubts?
I can't understand the last part of that how to just change the dimension or change the height. That's just one concern.
Okay, maybe Biraj can reply to this.
Okay. I will show you the demonstration. What I want you to do is just make the water level height same as this wall. Okay. So to do that, so I want to see the block and what it says, like what is the height of this, what it says. So in order to see that, I would go to the system and block mystic. So in that, so you can see the convert to meters is given 0.146. So what it does is it multiplies every value and makes it. So you can see like there is no number in this, right? So it got multiplied by 0.146 and that is the result explained here. So what is this height? So what is the height of this coordinate? I go to the, I would type the command paraform block, right? So click on apply. So see 17 and 13, right? If you subtract the coordinates of like y-axis 17 minus 13, then you will get the y-axis, right? You will get the height, right? So in order to do that, 13 and 17, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the y is 0. But for 17, 14, 15, 16, 17, the 17 y value is 0.32876. So you need to multiply this value 0.32876. So if you go to if you calculate here, so 0.3286, right, into 0.146 will give like 0.0479. So what you do is go to the set field and change the y value 0, 0, -1 and change this value, which is 0.0479. So now the water level will decrease. See, the water level is like, as you can see in the previous photo, you can see the water level is here. So I want to decrease it. So first block mesh, type the block mesh command, and after that set fields, and after that type interform to run the simulation. Now it's over. So let's go to the paraform. See, alpha.water. So it has been decreased. So in the previous image, the water level is at this height. Now I have decreased it. Now let's see the simulation. See, like few water will only cross over this bridge or over this wall. That is how we do it. So understood?
Yes, sir. Thank you, sir.
Okay. I hope everyone got it. So thank you.
So for today, we are ending the session here. Thanks a lot for joining and interacting so much. I hope it was a useful day for you also. So with this, I say bye-bye. Yeah. Thank you, everybody.